So it's a great pleasure to be here today with you at CIRM, in particular in this great place. And today I would like to share with you some ideas about how to combine some old estimator in extreme value theory, exactly the yield estimator, with the new and efficient machine learning algorithms. So we want to use the best part of the estimators, the well-known estimators, as well as the efficiency of machine learning algorithms. So this talk is based on two papers written with my former PhD student Arthur Maillard. So the first part would be dedicated to the yield random forest. So the main idea is to use the yield estimator, which is used to estimate the tail index of distribution. And this is a very old estimator. It had been proposed more than 50 years ago. And to use the machinery of machine learning, and more specifically here with random forest, to try to estimate not a unique tail index, but a tail index function. So we will use the idea of regression, but not to estimate the conditional mean, but rather to estimate the tail index function. And in the second part of the talk, I will present the second paper, tail index partition-based rule extraction. So the idea is to have a specific model for the tail index. Actually, we will assume that there exists a partition of the covariate space with a small number of subsets in which each the tail index has a constant value. So the main goal is how to estimate first the partition in the covariate space, and then to estimate the value of the tail index over each subset of the partition. So the first paper is rather a mathematical paper where we try to provide some theoretical results. It is well known that machine learning algorithms are very efficient, but actually there are very few papers which give some theoretical properties of this algorithm. And here we will try to give a uniform consistency result of our estimator. And the second one is more applied. We explain exactly what type of algorithm we use, and we also propose an application to tornado damage insurance. So, of course, this is not the only papers that try to combine actually extreme value statistics with machine learning. We can, for example, here give two other papers. So, for example, Maud, Olivier, and Sebastian propose a regression tree where specifically they assume that the distribution over the partition of the space of the regression tree are GPD distribution, generalized Pareto distribution, and they use for loss a maximum likelihood criterion to try to have parameters that are specific to this subset of the covariate space. And in another recent paper, Velto, Dombry, Kay, and Engelke, they propose to use the gradient boosting method to estimate not quantile, but extreme quantile of distribution. So let us start with the first part of the talk, so yield random forest. And I will explain you exactly what we want to do. So assume that we have a positive random variable z, and we will assume that we have also a vector of covariates of dimension p, here defined on 0 and p for because it is more easier. And we will make the following assumption. So the conditional survival distribution of z given x is a Pareto-like distribution. That is, you can write as z to the power minus alpha x multiplied by a slowly varying function, which is unknown. So here alpha x is what we call the tail index, and now it depends on x. So we want to have an estimation of alpha over the covariate space. So not one value, but now a function of the covariates. And L is a family of slowly varying functions. This function satisfies for each x the following asymptotic property. They are not known, and you have to try to mitigate the effect because you don't have exactly Pareto distribution, only asymptotically, that is, when you consider only the largest value of the sample, you are able to estimate the alpha x. And so what we want to do is to estimate alpha, or rather xi, which is the reciprocal of alpha. And for this, we have a set of independent random variables, dn, so of couple zi and xi, to estimate this function. In the statistical literature, there exists, of course, different approaches. Okay. First, a parametric approach, where it has been assumed that alpha x is equal to an exponential of a linear combination of the covariates. So you have to estimate a parameter of dimension p. So here it's not so difficult because the size of the parameter is finite, and you can use, let's say, quasi-maximum Likelihood estimator just by keeping only the largest observation and estimating by using the assumption that you have Pareto distribution, the value of theta. There exist also more people with weaker assumptions. So the summary parametric tail regression assumes that you have also an additional component. So you introduce a new function eta, which is unknown, and you try to estimate as well the parameter theta and the function eta by using, for example, splines to estimate this function. And in extreme value statistics, you have also what is called kernel tail index regression, where you use the kernel approach, that is, you are in a local neighborhood of the value of x, and you estimate with the usual estimator, but just assuming that the size of the neighborhoods tends to 0 as the number of observations tends to infinity. But here we want to have a global estimator. So not for a particular point x in the feature space, but for all the feature space 0 and p. So the first things to do when you want to estimate some function like the tail function, it is to only keep the largest value. So you have to define threshold. For the Hill estimator, you have only to define one threshold because the value does not depend on x, but now your alpha depends on x. So you have to define a function of threshold. So a threshold for which you will have a value for each x. So for this, we have a function t defined on the covariate space with positive value, and you multiply by a constant u that will tend to infinity as the size of the sample will tend to infinity. So you will have larger and larger threshold to selection your data. Actually, you define a subset of the observation, dn of u, so it depends on this parameter u. So this is the initial observation, but you only keep those for which z is larger than tu of x. So you only keep the largest value, but this depends also on the covariate. And then what it is done, in general in extreme value theory, it is to consider the normalized z. So you divide z by the threshold, you take the logarithm, and in this case, you are approximately close to an exponential distribution. That means you can prove that as the threshold tends to infinity, actually, the survival distribution of this variable tends to an exponential distribution with parameter alpha x. So the idea is to use the fact that you have an exponential distribution to try to estimate alpha. Not alpha exactly, actually, but the function alpha. So, as I explained previously, there is not a lot of papers that are able to give theoretical consistency results for machine learning algorithms. In the case of Breman's random forest, actually Scornebio and Ver, in a recent paper, proves that this estimator is L2 consistent. That is, they consider the regression framework with the L2 distance, so the quadratic loss, and then proves that uniformly over the space, the estimator is consistent. But they have some assumption. So they consider the following model: y is equal to a constant m of x, that is the expectation, plus an additive Gaussian random variable. So in this case, you see here that m of x is the conditional expectation of y given x. So this is a usual regression framework, but the random part is an additive component that you add. And they also have the following assumption, that is the function m is equal as a linear combination of unknown function mi of each xi. Okay, so it's a technical assumption to be able to prove that locally you are able to estimate your function m of x. Here we consider not the same framework, of course, because we know that we do not have Gaussian random variable. Actually, the best things what we can do is to approximate by exponential random variable. So what we want to estimate, actually, asymptotically, as the threshold tends to infinity, it is an exponential model. That is, we will write y as an exponential random variable multiplied by this unknown function xi of x. So the conditional expectation is still equal to xi of x, okay? But now you have a random variable which is necessarily positive, and moreover, the function xi must be also positive. So if you use the quadratic loss, you won't be able to have this property. So you have to choose an additional, another loss function. So this is exactly what we do. So instead of considering the quadratic loss, we will use the gamma deviance function. So the gamma deviance has been introduced this morning in the last talk. So it is a deviance that is the most let's say the best choice for gamma distribution, and here you have an exponential distribution. So this is actually the best choice you can do. And now the criterion is given here, and it is not a distance, so it depends on the observation y and as well as a parameter xi, and it is only defined for a positive observation, and it is only able to give you some positive value for your parameter, never negative value. And if you try to, this is a positive function, if you try to minimize this deviance, so the best choice here is to choose y equal xi. Okay, so you will try now to minimize such a deviance. So the estimators as we propose, the Hill random forest estimator, actually minimize not the sum of the square, but the sum of the deviance between the observation y I of u, so it depends on the threshold, and you consider so the deviation between y, the deviance, sorry, and your model f of xi. So you have now to define what is the class of function for f. And in this case, f is given in a class of function fn of u, which consists actually in a combination of tail regression tree. So tail regression tree is, well, we will explain exactly what it is, but it is a regression tree specifically for the largest observation. So you will consider a specific class of function to minimize this deviance. So first step, in the Bremer's random forest, you use actually a regression tree or cart. Here we will consider tail regression tree. So what we do is actually to consider only the largest observation. We use the deviance function instead of the quadratic loss, say, and we consider this deviance to split the space into subspace. So actually how it works, I think everybody knows, but you have, let's say that it is your covariate space, so 0, 1, 0, 1, two covariate x1, x2. This is a function, tail function defined here. Actually, your algorithms begins with the whole space, then decide to divide your space in two sub-rectangle, blue here and the complementary here, and then divide with this one and this one, divide this one, divide, etc., etc. And so you define here a tree, which here has several leaves, and you now not, of course, use the loss criteria, but actually the gamma deviance to define this split. So it is work actually you have a specific node, A, and you will split this node in two subnodes, A, L, and A, U, for which, how you do that, you have first to choose a covariate with index J, so xj, and then a position to decide if your covariate is larger or smaller than this split value. So actually, you maximize this criterion, which is equal as the difference between the deviance computed over A and the sum of the deviance computed for AL and NU, which weights depend on the number of observations you have in AL and NU. But it can be rewritten in this form very simply. So Y bar is only the average of your observation belonging to A. So here it is for AL, EU, and then you will choose the covariate J and the value Z, such as to maximize this criterion in each subset. So actually you do that iteratively, and you have to stop. So you stop the growth of your tree. You have several ways to do it. For example, you can decide to fix the maximal number of leaves that you want in your tree, or you can also decide to have a minimal number of observations in each leaf of the tree. So in this way, you stop the growth of your tree. So this is the first step, first to estimate a regression tree or tail regression tree, and then you have the irrandom forest where you will aggregate some other, let's say, regression tree where you will randomize the choice of the covariate as well as the choice of the data that you selection for your regression tree. So let theta be a random variable that is independent of the data, where you will use to choose a subsample of your covariate and a subsample of your data. Then you compute a regression tree. You do that capital M times, so for theta 1, theta m, you obtain M regression tree, and then you aggregate with an average to obtain a new estimator which is more robust. So here, actually the main difference with the Bremen random forest, which use the usual average to average over the regression tree, we use an harmonic mean. So we consider this is because for technical reasons, when considering an harmonic mean, we are able to be sure that when you aggregate a new regression tree, you minimize or you decrease the deviance of the observation. You have two additional parameters. First, n-try, which is a number of covariate you want in your subsample, as well as an, which is a number of data you need for your regression tree. So now you have 4 hyperparameters that you use to estimate. And what we want to do in this paper, actually it is a paper with a lot of mathematics and proof, it is to show that when you do that, you have a consistent estimator. But not a local consistent, that is not for a specific value of your covariates, but over all the covariate space, that is, you have to integrate with respect to all the value of x. So it's actually the criterion that we choose is to compute the deviance between the true value, the true function, and the estimated function. So we then average over all the possible value of x with respect to the distribution of x. So this is the criterion that we want, and this is more difficult than in the case of the Bremen random forest, because now you have an additional constraint, that is you have to choose the largest value. Remember that in the first step, you do not consider all the values, all the observations, but only those for which Z is larger than the threshold TU. So you have to choose a threshold. You have also to have enough observation to satisfy a consistency result. And you need additional technical conditions that I do not want to discuss to prove this result. So actually, under the condition that the slowly varying function has the following form, we are able to prove this D-consistency result. So now we have an estimator which is consistent not for one point, but over all the space, which is a very interesting result. But we do not know the rate of convergence. We knew that this tends to 0, but actually we don't not know what is the rate of convergence. So this is the main theoretical result here. And we also provide in the paper some numerical experiments. So quickly, here we consider two covariates over 0, 1, 0, 1. We assume a quadratic form for the tail index function over this space. We have a family of slowly varying function with a parameter m, which gives you the idea which you are close or not to the parameter, to the Pareto assumption. That is, when m is equal to 0, you have exactly a Pareto assumption for a distribution. And then in this case, you can keep all the observation because you are exactly in the asymptotic limit. Otherwise, when m increase, you are more and more, you deviate more and more from this assumption. And actually, you will have to choose a threshold which is larger and larger. So the choice of the threshold is actually a very important thing to do. So there was a method that has been proposed by Wang and Tse. So Wang and Tse are the two authors who proposed the tail regression. That is by specifying a parametric form for the tail function. But they also propose a method to choose this threshold. So this is the following things. Actually, when you have estimated a model for a specific threshold u, you try to normalize your observation. Actually, you take your y, you divide by the estimate, then take the logarithms and minus the logarithms. And if your model is the right model, you should have uniform distribution. So you will then compute L2 distance between the approximation of u with respect to the quantile of a uniform distribution. And then you choose a threshold for which this distance is the smallest. Okay, so this defines this u star. Or not. So here you have several graphs that can explain you how the optimal choice of this threshold depend on the level of m. Well, let's see. Ouais. Ouais, mais. Bah, il est bien sur ma main, mais je crois qu'il n'y a plus de pile, quoi. Alors, ouais, bref, il n'y aura pas de pointeur. Bref, you have different size of your sample, 4,000, 10,000, and 20,000 observations. But, well, I don't have time to talk too much about that. Actually, here you have the bias of the estimators. So when m is small, the bias, of course, is larger. When the number of observations increase, the bias decrease. And actually, you have a very small bias for the largest n. When n also increases, so it is more difficult to estimate the tail parameter. So actually, the bias is larger. This is more or less the same story for the root mean square error, when you can show that when the size of the population actually increases, so the root mean square decrease as expected. So we have a theoretical reason, and on simulation, it is also very, very efficient. Now, the second part of the talk. So it is a more applied paper. So the aim here is to be able to propose an estimation of a function, but only by assuming that the tail function takes a finite number of values. Actually, we assume that the covariate space is divided over a partition P. So AI are the subset of the partition. And on each subset, the tail function takes only one value, alpha I. So the goal here is to first estimate this set alpha I. And once you have estimated this set, you will estimate the parameter alpha I. So it is not so easy because you have to estimate some maybe potentially complex shapes of subset. But actually, when you have estimated in an efficient way this partition, the estimation of the tail function is not so difficult because it is actually only an average, let's say, of the value that you have over this space. So we propose what we call a tail index partition-based restriction method. So the aim is to be able to say when X belongs to some subset of the space, you give a very specific value to the tail function. So 2 steps. The first step is to use what we call an additive tree ensemble, which, for example, is what is done by the hill random forest. So actually, when you do that, you obtain a very fine partition of your space, of your covered space, with very small rectangles. So you divide 0, 1, P into very, very small rectangles for which you have different values, because this is an aggregation of different, let's say, regression tree. And the goal then is to be able to aggregate these small rectangles to reveal the partition that you want to try to estimate of the subset AI. So this is the second step. We use a hierarchical clustering algorithms where we have to put some additional constraints, some spatial constraints, to be sure that when you aggregate the small rectangles, they are close from each other. So you need to be sure that the set, the cluster you get, actually are connected set. Otherwise, you could have very large value, a number of small rectangles which are all over the space, and it will be not, of course, interesting. So here we assume that actually you have a partition and you need to reveal this partition. Okay, so this is a mathematical expression of what a hill random forest provides. So you have a partition of very small rectangles, B, and over this B, you compute an estimate, Bj of n, which is the aggregation over all the tail regression tree. Then the second step, so now we have to gather these small rectangles, and we decide to use what is known the cluster geo algorithms, which is actually a word-log hierarchical clustering algorithms where you consider spatial constraints. So how does it work? Actually, in the usual word hierarchical clustering, you have a dissimilarities matrix for the features. And now you add a new dissimilarity matrix, which takes into account the distances between the rectangles that you want to aggregate. So in this case, you can put more or less weight to have more or less connected cluster as the final step of your clustering algorithms. So gamma is the weight between these two dissimilarity matrices, and you have also to choose actually this value. We also propose in the paper a surrogate model. That is a model that is proposed to help you to explain how the subsets are estimated. Actually, you could have a very complex shape for your subset, and this is not necessarily easy to understand how the covariates have interacted such that to give these shapes. So it is, as usual, for very complex machine learning algorithms to propose an explainable model, a surrogate model, that will give you some intuition, very simple intuition, what are the results of your complex algorithms. So I do not have time to give more details, but actually it can be very helpful to understand exactly the results that you get for more complex data set. So I would like first to propose you some two toys example. So actually we will understand exactly if you do the good thing or not. So we have two sets of data. For model 1, actually, we have a tail function with 4 values for the 4 quarters of the square 0, 1, 0, and 1. So 2, 3, 4, and 5. And actually, for a regression tree, it's not so difficult to estimate such a shape, because the tail regression tree actually splits the space with horizontal or vertical lines. So it's not an easy, it's not a difficult task to estimate such data. The second one is actually more difficult. We assume that we have nested disk, where the value of alpha change. So in the center, you have the value 2, then 3, 4, and 5. But it's here very difficult, because you have to be able to split your space with line to obtain circle. So it's not easy. So the first step, so the additive tree ensemble, which here is given by the tail gradient tree boosting, give the following result. So actually, you can show the value of the prediction with the color, red, yellow, green, and blue. And you can also show, you can also see the lines that are used by the regression tree to split the correct space. Okay? That we have, I don't remember exactly, maybe 100 regression tree. Each use some specific lines, and when you aggregate your estimator, you obtain what we call a cross partition, where you divide actually the whole space into very fine partitions, so there is very small rectangles. Okay, and now the goal, the second step, will be to aggregate these small rectangles to be able to show the true picture. That is the actually 4 sub-square, red, yellow, and blue. So in the first case, actually, you have a very good estimate. It is not the case for the second example, but actually you can see, well, more or less the shape of the disk. And now, in the second step, use the hierarchical clustering algorithms. So you have to choose first the value of gamma, the weight for the special constraint. If you were more special constraint, you put gamma close to 1. And then you have also to choose the number of clusters that you want after your clustering algorithms. So you can choose first the value of gamma. You have several what we call fidelity curves, which give you for each partition the value of the R2 measures between the prediction of your gradient boosting algorithms with then the value of you obtain after the clustering algorithms. So when you have more and more and more cluster, of course the quality of the aggregation is close from the initial observation. So here we choose gamma equals 0.3 for the first set of data and 0.1 for the second one. And the fidelity is quite good, or very good for the first one, and a little bit less for the second one. And this is actually what we get after the clustering algorithms. So in the first example, we reveal actually very well the first 2 squares, sub-square, but not so easily the last 2 squares, because alpha was equal to 5, to 4 and 5. And since we estimate psi, which is the reciprocal of alpha, the difference between both are small. So it is more difficult to be able to discriminate between the 2 values for the 2 subsquare in the lower part of the graph. And for the second example, here you obtain what we saw. So a first cluster in red, and then something which is more or less close to the initial nested disk to reveal actually the true partition. And to be sure that we do something which has sense, we also compare the distribution of your observation in each cluster. Actually, as I said in the beginning of the talk, we should have an exponential distribution with a parameter equal to alpha x. And here alpha x, you have only 4 values, depending on the cluster you have. And so we propose here some QQ plots comparing the distribution of the observation with respect to the distribution of an exponential distribution. And if you do something which has sense, actually you should have lines on these QQ plots. And this is what we actually obtain here. So this is a surrogate, but I skip it. So to finish, the real case study. So we propose an application to tornado insurance. So we have the chance to have a tornado data set from the National Oceanic and Atmospheric Administration from the US, containing approximately 60,000 events from 1950 to 2011. And we have a lot of information, and we kept, for example, the length of the tornado, its width. Mag is for the size of the L in inches. We have the longitude, latitude, the state, the date, and then some information to compute the value of the damage. So we combine the two last variables to propose a new variable called property damage. We give you the damage amounts for each tornado. We retain only strictly positive amounts, so we get approximately 40,000 observations. Then we decide to adjust this amount for inflation, not to be biased by inflation effect. Then we also get the year and the month, and we also decide to divide by the density of the population over the US, because we think that where you are in region with an area with a very high density population, you will have, of course, large amount. So we have the information of each county in the US, and we decide to propose a new variable, so damage by density. We divide the property damage by the density, and we will try to estimate our model on this data set. So here two graphs. You show the linear dependence between the logarithms of the length of the tornado with respect to the log of the damage, or the log of the width with respect to the log of the damage. So we have here an intuitive observation. What we have to say is that we do not propose our model on the observation, but actually we perform a deterministic transformation. So we have a one-to-one transformation to put our data in our framework, that is with Pareto type distribution. So we transform it by exponential of the damage to the power 1/4. And then we use also our procedure. So the aim is to divide the correlated space into subsets and to estimate the tail index for each subset. Okay, so usually we have a training set, a validation set. We estimate for the first step a Taylor tree boosting. We use a 5-fold cross validation, etc. It is classical. We choose, after looking at these fidelity curves, that gamma should be equal to 0.1, and we decide to keep 12 clusters to divide the correct space, so into 12 values. Here you have, for each of the 12 clusters, the distribution of the prediction of the gradient boosting. So for cluster 1, actually the value of the tail index is approximately 0.37, and you have the distribution of the prediction over this subset. So you expect that to have something which is not too spread, okay? And you can see that you have a clear here separation of the value from 0.37 to 3.70. And to be sure that we do something which is pertinent. So we have the 12 cluster and the 12 QQ plot. So we compare the value of the data after, of course, all the normalization needed with the exponential distribution. So we observe straight line. So it is a very good point to say that our model makes sense. And on the other graph, you have some box plots for each of the covariates. So you consider the 12 cluster, and you have the box plots for each cluster of each covariate. Okay, so you can see here that the latitude and the longitude are very relevant feature to explain this tail index. You have a very only increasing or decreasing shape. It is not so clear with other covariates. Here it is only the trees that we get with the surrogate model, so we are able to explain more easily how we obtain the 12 cluster. So you divide first with respect to the length, width, year, etc., to define exactly how you get this 12 cluster. So to conclude, just to say that, of course, estimating the tail index is something which is not easy when you have only a random variable. But now if you have a family of random variable with a covariate, that is, you have a family of conditional distribution, it's really difficult. But we can still propose some approaches. And it is very important to have good risk assessment to be able to manage this tail index with respect to the characteristics of your customers or for your policy holder. So we also propose an approach that is able to split the covariate space into subsample, into subsets, for which you can have explanation as well different value to explain a very simple way the tail index function. Well, that's the main messages, I think.